Hello and welcome to another video lesson with Mr. Roman. Today we're going to be talking about the notes for the side angle side similarity theorem. And we need to do a little bit of review. Thus far we've talked about the SSS, or the side-side-side similarity theorem. We've talked about the AA, or the angle-angle similarity theorem. And today the new one is going to be SAS, which stands for side angle side. And so let's look at the first review problem that you have on your notes. Here you have two triangles, and you know all three sides of the triangle. So here's a case where you would want to use the side-side-side similarity theorem. And you want to set up three ratios. So you want to set up the longest side to the longest side, the middle side to the middle side, and then the small side to the small side. And so let's look at those ratios. 21.25 over 8.5. That's got to be equal to 17.5 over 7, and that's got to be equal to 15 over 6. Now when you do the ratios there and you divide each of those, you'll get that the ratio is actually 2.5 for each of them, the red, the green, and the blue. So we could say, yes, these two triangles are in fact similar. So we would write our similarity statement as this: triangle ABC is similar to triangle DEF. And that is by, the way we're saying that's by is by SSS, or the side-side-side similarity theorem. So we're checking all the sides to see that they're proportional to each other. Okay? Let's go ahead and look at number 2. In number 2, we know that we don't have enough information to use the side-side-side theorem because we don't know the side XY or RQ. And so instead we need to use the angle-angle similarity theorem, which says we've got this pair of congruent angles here with Y and Q, and then we have this pair of congruent angles with X and R. So then we would be able to say that triangle XVY is similar to triangle RSQ by the AA similarity theorem. So by the AA similarity theorem. And then lastly, this is where we're going to break into our new topics. We have two triangles here, and we don't know the third side here, which is QT and PV. And so we cannot use the similarity theorem with SSS, or side-side-side. And we do not know enough information about the angles here, 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 and here to be able to say anything about the angle-angle similarity theorem. So what we need is a different theorem that involves angles and sides together. And that's what the SAS represents. So we're looking for two sides that are going to intersect at a congruent angle in both triangles. So the two sides are the green and the red here. And they both intersect at that congruent angle with the box, which is 90 degrees. So the side connects to the angle, connects to the side on both triangles. So, but we have to check to see if those sides are actually proportional to each other in each of the triangles. So we would set up a ratio of 24 to 18 equals 28 to 21. And when you find those ratios, you'll get that they are 1.3 both repeating. So they are in fact similar. Now an interesting point here to make is that using this SAS theorem, you would not be able to say anything if, let's say we didn't know that these two angles here were not 90. Let's say we knew that this angle was congruent to this angle in these two triangles. Well, the SAS theorem has to connect the two sides that are in question. So notice the angle that they're connecting at is here and here. We would not be able to use the SAS theorem here and set up the same ratio of 24 to 18 is equal to 28 over 21. And then use the angle T and use the angle V as our two congruent angles. That would be incorrect. Because again, they're not connecting the two sides that we're looking at to be proportional. And so they have to be connecting. So in written words, the side angle side theorem for triangles would be this: if two connecting sides of a triangle are proportional to two connecting sides of another triangle, and so you also have to have the and there, and the angles that connect them are congruent. Then the triangles are similar. So let's look at that last example here. What that means as far as in context. In order to use that similarity theorem, you have to have two sides connecting at an angle that is congruent on both triangles. So the angle that's congruent in both triangles is the green angle here, or the 90-degree angle. And the two sides have to connect in that place in both triangles to use this theorem. Okay, now let's flip to the back side on your notes. Example 1 looks like this. And here we can go through our list and say, well, we cannot use the SSS, the side-side-side theorem, because we don't know the third side here and here. And we can't use the AA theorem, the angle-angle theorem, because we don't know enough about the interior angles here, 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 and here. We don't know anything about those. So our only other option is to use the SAS theorem. And notice that the two sides that we're going to be looking at all converge at that 42-degree angle. So this is congruent with this. So then, yes, we can use this theorem. So we'd set up a ratio of 20 over 16 is equal to 15 over 12. Then when you find that ratio, you're going to find that it is going to be 1.25 for both of those, which does in fact make them similar. So then our similarity statement would be this. Triangle MLP is similar to triangle HKG. HKG. Okay? Let's look at example 2. So example 2 looks like this. And in this situation, you could actually use the SSS, or side-side-side similarity theorem. And mainly, you could do it like this. You could set up the biggest side of this triangle, which is 20, over the biggest side of this triangle, which is 15. So 20 over 15 is equal to the medium side of this triangle with the medium side of that triangle. So 16 to 12 equals the small side of this triangle here. So the small side of this triangle is 12, and then the small side of that triangle, so 12 over 9. And you would find that all of those ratios are equivalent, and they all come out to be 1.3 repeating. So then you could say by side, side, side that these two triangles are similar. Now, that's if we know all three sides. Let's go ahead and delete some of the information to start the problem here. And let's imagine that we didn't know that the 20 was there and the 15 was there. Well, then we would have to know, first of all, that this angle is 90 degrees. And then we would have to use our side angle side similarity theorem. And what I went ahead and did, I flipped the triangle over. And I made it so that you could see it a little bit easier, what those angles are going to look like. So this is the two triangles. When you flip them, and their corresponding parts are matching. So go back to the diagram. Turn this triangle here. You want to turn it 90 degrees to the right. And that will give you this triangle down here with the W. And so now SAS says that we can do this. 16 over 12, so that would be this to this, is equal to 12 over 9. So this to this. And again, those both come out to be 1.3 repeating. So based on SAS there, we could say that these two triangles are, in fact, similar. Let's look at example 3. In this triangle, we know that the angle C here is going to be, we have vertical angles here and here that are going to be congruent. And then the two connecting sides, of course, are the 30 and the 15 on this one, and the 18 and the 9 on this one. So we can use SAS, side angle side, and the ratio we would set up would be 18 over 30 is equal to 9 over 15. And when you divide both of those, you get a ratio of 0.6 repeating. And so then we would say, yes, these are similar by the SAS theorem, side angle side theorem. And the last example you have, on your notes there, you want to change that 5 down at the bottom corner to a 15. I'm sorry, the 15 to a 5. So that was a mistake on my part. And then we need to find out if the two triangles are similar. And here we cannot say anything about the angles here, 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 and here, mainly because we don't know that these lines are parallel. We don't know anything about them being parallel. And so we cannot say that they're congruent. So that rules out the angle-angle similarity theorem. But maybe a way to look at this a little differently would be to draw the two triangles separately, and that's what I did down here. And so you see that the F angle is actually shared on both triangles. So F, being this angle right here, is shared on both triangles. So that's the common angle that's congruent to both of them. We know it's congruent. And so the two sides obviously are converging at that angle. So we can use side angle side and set up the ratio of 6 over 9 equals 10 over 15. And when you do the calculation there, you'll get that both of those ratios come out to be 0.6 repeating. And so yes, you could say that these two triangles are in fact similar. And our similarity statement would be this. Triangle FGK is similar to triangle FHJ. I think we forgot to do the similarity statement here on number. So this is number 2. The similarity statement would be this. Triangle WXY is similar to triangle YXZ. And then the similarity statement on this one would have been triangle CAB is similar to triangle CDE. CDE. All right. That concludes our notes for the side angle side theorem. And come tomorrow to class with questions.